We can start with the presentation by Bertrand Baudouy, and he will tell us about the technological achievement of SR2S.
So, for the superconducting cable development, as you know, for space application, the weight of any component is very critical. And usually for superconducting magnets, whether it is for terrestrial use or even for terrestrial use, but especially for space application, the conductor is a relevant part of the mass budget. So the average mass density of the conductor must be as low as possible. Starting from that, INFN and Columbus work on the development of a lighter MgB2 conductor, and they started from a nickel matrix MgB2 tape and change it to a titanium matrix MgB2 tape to make it lighter, still strong but lighter. And you can see the result. They almost double, after 3 years of work, they almost double the critical current, which means that they almost double the current performance of the cable, which is a very great achievement. So that was done on small length system. And now to build a magnet, what you have to do is you have to produce kilometers of tape to wind the magnets, and that they have been working on that with this titanium matrix MgB2 plus copper for stabilization for a better running. Then they have already achieved 360 meters of this conductor, and they have also characterized as a function of the temperature the critical current of this tape. It's the way to protect the superconducting magnets. The protection is to avoid the destruction of the magnet against perturbation, of course, but also to keep him as much as possible always superconducting. You imagine that if the superconductor goes to the normal state, then it will lose its property, and then of course the magnetic field will not be present anymore, and therefore the astronaut won't be protected. So we try to imagine scenarios to protect the magnet against the quenches. A solution has been proposed to keep the temperature below 170 Kelvin when the magnet warms up after a quench, to keep also the maximum temperature at sometimes 300 K, at certain points of 300 K, and the voltage between 1000 volt. We came up with an active protection scheme, which means that we were using, I'm not going to go into too much details, but we're using the coil plus a heater and a superconducting switch just to warm up nicely the entire magnet. In subdividing the magnet in, you can see 330 subdivision. And this solution makes this protection scheme lighter, only 10% of the mass of the coil, and a better, lighter than the direct the solution, which means that warming up the entire magnet. The hotspot temperature is very low, 170, and the damping time, which means that the time to get rid of all the current to avoid burning the magnet, is very small. So the cryogenics design is a combination of the space and terrestrial technology. Outside, we have a sun shield that looks like, that is exactly like the Hubble sun shield that we recalculated, and they can screen the heat coming from the sun. But inside, the human habitat must be regulated around 300 K, of course, otherwise the astronaut will be a little bit cold. And this part is radiating heat to the superconducting magnet. And we had to imagine an internal shield cooled at 80 Kelvin nitrogen temperature. We propose to cool this thermal shield. We propose to have a cooling source, a renewable cooling source. Those are machines that are called cryocoolers. They are thermodynamic machines powered by electricity. So we have electricity on space with radiation, the sun. And also we propose an innovative thermal link which called the pulsating heat pipe. You can see on the side, but I don't think it's going to, the movie is working. So to cool down the entire magnet, which is about 10 meters long and several meters in diameter, you need to have long PHP. So far, only few PHPs have been tested at low temperature, and they're very small, tiny length. We propose to extend this length to several meters, which will be the longest cryogenic pulsating heat pipe ever tested on Earth. So we designed a long experiment. You can see the cryostat here, and on the side those pulsating heat pipe with those small tiny tubes that you can imagine. So to conclude the talk, I will say that for the superconducting cable development, a new cable, MGB2 light cable has been developed. This conductor is a base, can be considered as a starting base for conductor for the future space application. It has already, this conductor is in an evaluation for X-ray space telescope project. For the superconducting magnet protection, we have developed an active protection scheme based on superconducting switches, and this protection scheme can be applied to any modular cold magnet, so it can be used for other terrestrial magnets that we can be working on. And for the innovative cryogenic heat pipe, we are going to test and have first result on the longest cryogenic PHP system ever tested. And this PHP-based cryogenics has been already proposed for the European project FET Open called NEEDS. So we're going to wait for the result very soon. If we are, and also we have also proposed this cryogenics type of system for a project called Special Magnet for a Super-FRS project at GSI in Germany. That's it. Thank you very much for your attention.